Imagine trying to run like a hyper-complex particle-level physics simulation natively on a standard smartwatch.
Right, you just think it's impossible.
Exactly. I mean, in machine learning, we've basically been conditioned by scaling laws to believe that if you want God-tier reasoning capabilities, you fundamentally need a trillion parameters and a data center the size of a city block.
Yeah, the thermodynamics of compute.
Right. You want a brighter star. You just need more mass. But what if we have been fundamentally misunderstanding what reasoning actually weighs? Welcome to the Deep Dive. Today, we are dissecting a brand new technical report from Sina Weibo Inc., and this is dated June 15th, 2026.
Fresh off the presses.
Yeah. It is titled VibeThinker-3B, Exploring the Frontier of Verifiable Reasoning in Small Language Models. And just to set the stakes for you right out of the gate, our mission today is to provide a comprehensive professional breakdown of how a strictly 3 billion parameter dense model achieves frontier-level performance on highly demanding verifiable tasks.
And to frame the significance of this for your own ML workflows, I mean, this paper represents a massive structural challenge to traditional scaling laws.
Oh, absolutely.
We are looking at a 3B model matching, or in some cases, exceeding flagship models that are literally 200 times larger. I mean, we're talking about DeepSeek V3.2 at 671 billion parameters.
Right.
GLM-5 at 744 billion Gemini 3 Pro. And the authors aren't relying on massive compute and inference. You know, they engineered a highly novel training pipeline.
Yeah, which is what we're really digging into.
Exactly. We'll be looking closely at their curriculum-based supervised fine-tuning, the maxing-guided policy optimization, long-to-short RL, and this really cool claim-level reliability scaling. We are skipping the broad industry speculation today to focus entirely on the mechanics of this extreme parameter efficiency.
Okay, let's unpack this. Because before we deconstruct the actual training pipeline, we really need to understand the theoretical shift that motivated the authors to push a 3B model this far in the first place.
Yeah, because you can't engineer a solution if you're operating under the wrong assumptions about capacity.
Right.
So the foundational concept the authors introduce here is the parametric compression coverage hypothesis. In the field, practitioners usually treat all model capabilities as roughly requiring the same kind of parameter scaling.
Like it's a one-size-fits-all curve.
Exactly. But the authors posit that foundational capabilities actually differ in the structural form of their parameter demands. So on one hand, you have open domain knowledge and general-purpose competence.
Okay, so think of scoring high on a benchmark like GPQA Diamond.
Right, which tests graduate-level physics, chemistry, and biology.
Yeah.
That requires expansive parameter coverage. The model physically needs the weights to memorize massive amounts of facts, domain-specific concepts, and incredibly long-tail semantic associations.
So, to use an analogy for you, open domain knowledge is essentially an unstructured database. It fundamentally just requires raw storage volume to map all those semantic connections. But verifiable reasoning, like advanced mathematics, formal logic, or competitive coding that feels structurally different, it's more like a highly optimized algorithmic engine.
Right, like a quicksort script.
Exactly. A quicksort script requires minimal storage, but extremely high execution precision. Verifiable reasoning relies on search, constraint satisfaction, error correction, and multi-step composition within very structured spaces.
And taking that quicksort analogy further, if you bloat an algorithm with unnecessary parameters or extraneous data, you just introduce latency and potential failure points.
Yeah, that makes sense.
Reasoning requires strict execution paths. So the hypothesis here is that this capability can be highly compressed into a compact reasoning core. This is what they call the reasoning knowledge decoupling paradigm.
Meaning small language models are no longer just compute-saving fallbacks for cheap edge deployment?
Exactly. If reasoning and knowledge are truly decoupled, these small models represent a complementary evolutionary trajectory to massive scaling laws. They can be trained as highly specialized reasoning instruments.
Okay, but building that logic engine from scratch means standard supervised fine-tuning, or SFT, isn't going to cut it.
No, not at all.
We need to look at how they engineered the initial spectrum-to-signal SFT phase to build that foundational logic. Let's look at their curriculum-based two-stage SFT strategy. Because stage one is, well, it's designed for broad capability coverage.
Yeah, stage one uses a mixed domain data set, so math, code, STEM, general chat. To maximize the diversity of task types flowing into the gradients, they employ sequence packing with a global batch size of 128, and the learning rate decays to 8 times 10 to the negative 8.
Which establishes a highly stable baseline.
Right, but the real architectural pivot happens in stage 2, which shifts entirely to a hard reasoning subset.
And the filtering on stage 2 is brutal. I mean, they drop any reasoning traces shorter than 5,000 tokens outright.
Gone.
Yeah, and then they use their previous 1.5B model as a reference judge. They run 8 independent rollouts per query through that older model and filter out any training data where the error rate is below 0.75.
Which is wild.
It is, meaning they only train on problems that the previous model failed on over 75% of the time. They are forcing the network to concentrate exclusively on long-horizon logical derivation and complex constraint satisfaction.
Well, the intuition is that you cannot teach advanced reasoning by showing a model trivial proofs. It has to learn the structural dynamics of recovering from deep logical dead ends.
Right, but here is where any ML practitioner listening is going to spot a massive red flag.
Oh, the mode collapse.
Exactly. If you aggressively train on highly filtered optimal trajectories in SFT, you almost always trigger mode collapse. The model's output variance basically drops to 0 because it learns a single rigid way to format a response.
Yeah.
And if your model only generates one type of response, you completely starve the subsequent reinforcement learning phase. I mean, RL requires a high variance landscape to explore, right?
Yeah.
Otherwise, advantage estimation fails because every generated trajectory looks identical.
The authors actually anticipated that exact mode collapse scenario. This is the core of their diversity exploring distillation technique.
Yeah. Okay, break that down.
So the whole point of the SFT stage in their spectrum to signal paradigm is not to find a single optimal path, but to build a broad solution spectrum.
Right.
Instead of conventionally picking the single checkpoint with the lowest validation loss or the highest pass at 1, which measures if the top-ranked response is correct, they ran periodic evaluations of intermediate checkpoints.
So they evaluated them using pass at K on domain-specific probing sets, looking at the top K responses to measure generation diversity.
Exactly. They are hunting for checkpoints that naturally produce a wide variety of valid solutions, not just the single most efficient one.
Oh, wow.
Yeah, and they identified several of these specialist checkpoints throughout the training run that demonstrated high variance in their correct reasoning traces. Then they merged them at the parameter level.
So by averaging the weights of these diverse checkpoints, the resulting model preserves the spectrum of varied reasoning paths.
Yes, it essentially banks a rich, high-variance landscape of logic, ensuring the RL stage has enough behavioral diversity to explore and amplify later.
Okay, so we have a diverse SFT landscape, but a diverse landscape is just a playground. When the model moves to the reinforcement learning phase to amplify the correct signals, we run into the classic RL frustration.
Yeah, saturated signals versus sparse signals.
Exactly. In standard RL frameworks, prompts that are too easy provide saturated signals. The model already knows the answer, so the gradient update is 0. Prompts that are too hard provide sparse, noisy signals. The model just generates garbage. And again, you learn nothing.
And that phenomenon is exactly what Maxent Guided Policy Optimization, or MGPO, is designed to solve. It is their core RL backbone. MGPO dynamically assigns weights to prompts based on their empirical correctness compared to a maximum entropy point.
And the maximum entropy point in a binary correct or incorrect scenario is
0.5.
Right. A prompt where the model gets it right exactly 50% of the time.
Right. So the system calculates the empirical group accuracy over a sample of responses for every prompt. Prompts with intermediate correctness where the policy is unsure, meaning it is operating right on the edge of the model's current capability boundary, receive exponentially higher weights.
Okay, so the weight scales based on how close the empirical correctness is to that 0.5 point.
Exactly.
By doing that, they are focusing the gradient updates precisely on the boundary where the model actually has something to learn, which stabilizes the training and mitigates over-optimization on high-probability tokens.
Yeah.
But looking at their multi-domain reasoning RL setup, there is a glaring anomaly in the paper.
The context window.
Yeah, standard practice in reasoning RL is progressive context window expansion. Practitioners usually start with high truncation, maybe a 4K or 8K window to save massive amounts of compute and filter out the model's tendency to babble early in training. Then you slowly expand the window as the model gets smarter. But the Weibo team completely abandoned this and dropped a single 64K long context window right from step 1. Given GPU hourly costs, dropping a 64K window on an untrained RL policy is the kind of compute budget nightmare that gets engineering teams fired.
It really is. But here's the thing. The authors actually used progressive expansion in their previous 1.5B model, and it performed adequately. But when they applied it to the 3B model, they discovered it caused irreversible degradation in reasoning performance.
Wait, really? Irreversible.
Yeah.
And the root cause traces back to that incredibly strict data filtering in SFT stage 2. Because they only trained on traces longer than 5,000 tokens, the 3B model's initialization checkpoint was already exceptionally strong at long horizon thinking.
Exactly. So truncating the context to 4K or 8K early in the RL phase didn't remove noisy thinking traces because those traces were already highly coherent.
Oh, I see.
Instead, it forcefully truncated and destroyed existing high-quality, long-horizon reasoning behaviors. The model essentially learned to prematurely terminate complex logical chains just to satisfy the artificial window constraint.
Wow.
Yeah, they proved through ablation studies that with a strong initialization, full context RL, using that 64K window from the very first gradient update, preserves complex trajectories far better than progressive expansion, which completely justifies the massive upfront compute cost.
It makes total sense. By forcing a short context early on, you are actively untraining the model's ability to think deeply.
Right.
So the RL phase successfully taught the model to think deeply, using a massive context window and boundary-focused gradient updates. But anyone who has deployed a reasoning model to production knows that long chains of thought, even if accurate, can quickly become highly inefficient.
Oh yeah, they start babbling.
Exactly. The model might take 10,000 tokens to solve a problem that only requires 500, wasting inference compute. How did the team optimize token efficiency without destroying the reasoning accuracy they just spent millions of GPU hours building?
Well, they implemented a dedicated long-to-short math RL stage. They transitioned the objective function from optimizing purely for accuracy to optimizing for token efficiency.
Okay.
For every prompt group, the system determines which trajectories arrived at the correct answer. Then it applies a zero-sum reward redistribution strictly among that correct subset.
And the mechanism here is critical for anyone building proximal policy optimization pipelines. For every correct trajectory, they calculate a brevity score, denoted as S sub I, which is simply 1 divided by the length of the response, L sub I.
Right.
Shorter correct responses get a reward boost, longer correct responses get a penalty. But because the shifts are centered, their sum is exactly 0 across the correct subset. Let's make that concrete. Imagine 3 correct trajectories for a math problem. One takes 10 tokens, one takes 50 tokens, one takes 100 tokens. Because this reward mechanism is strictly zero-sum, the 10-token path isn't just getting a generic arbitrary bonus, it is mathematically stealing reward probability from the 100-token path.
Exactly. And the brilliance of the zero-sum design is how it interacts with the advantage estimation in PPO.
Yeah.
If you generically penalize length across the board, you would artificially deflate the overall value function baseline for that prompt.
Which destabilizes the entire training run because suddenly the model thinks getting the right answer is a bad thing just because it took a few extra tokens.
Right.
The gradient mathematics get completely scrambled.
Yeah, by using a zero-sum redistribution only among the successful attempts, the mean reward of the group remains perfectly flat. The overall advantage estimation is preserved, but the model's internal preference is forcefully reshaped toward the most concise, successful path.
That's incredibly elegant. So after optimizing for efficiency, they moved to offline consolidation to lock in the weights.
Yes, they perform offline self-distillation, pulling the best trajectories from the math, code, and STEM RL stages. And they don't just randomly sample.
Right.
They filter the teacher traces using a learning potential score, which is based on the length-normalized negative log likelihood of the trace under the student model.
Meaning they measure how surprising a particular correct trace is to the current version of the model.
Exactly.
They prioritize teaching the model the successful logical paths that it currently finds the most difficult to predict, maximizing the information gain of every distillation step.
Right. And the final step in the pipeline is instruct RL, using rubric-based rewards and strict rule-based constraint checking for formatting, ordering, and keyword inclusion.
Which is a vital sanity check. Highly optimized reasoning models often lose their ability to simply answer a basic user query without launching into a massive chain of thought.
Yeah, they just ramble.
To verify it remained controllable, they tested it against IFEval, a benchmark specifically designed to measure strict instruction following capabilities.
And it scored a 93.4 on IFEval, proving that the extreme reasoning enhancements in the long-to-short and MGPO phases didn't override its basic utility as an assistant.
All right, we've traced this incredibly rigorous multi-stage pipeline. Now, what does this highly compressed 3 billion parameter reasoning core actually achieve when we test it against the giants?
Well, the performance metrics on verifiable domains fundamentally rewrite our baseline expectations for a 3B parameter budget. On AME26, the American Invitational Mathematics Examination, VibeThinker-3B hits a 94.3.
Wow.
On LiveCodeBench version 6, evaluating modern competitive programming, it achieves an 80.2 pass at 1. On HMMT25, the Harvard-MIT Mathematics Tournament benchmark, it hits 89.3.
I mean, for context, that 94.3 on AME26 puts a 3 billion parameter model neck and neck with DeepSeek V3.2, a 671 billion parameter architecture.
That's great.
And Kimi K2.5, which is pushing the 1 trillion parameter boundary.
Yeah, and the authors also designed a rigorous out-of-distribution generalization test to ensure the model wasn't simply memorizing the training data.
Oh, good.
They scraped unseen, execution-verified LeetCode weekly and bi-weekly contests from April and May of 2026.
So data that mathematically could not have been in the pre-training or SFT mix.
Exactly. And the model achieved a 96.1% acceptance rate on its first attempt Python submissions. It passed 123 out of 128 problems without a single revision. That firmly beats out much larger frontier models like Qwen 3 Max and Claude 4.6.
That is wild. The paper notes they managed to push that AME26 score even higher to a staggering 97.1 using test time scaling. But they didn't use standard majority voting.
No, they didn't.
Because in majority voting, you force the model to generate 32 or 64 full reasoning traces, and then you just pick the most common final answer. It works, but the inference compute cost is astronomical because you are processing tens of thousands of tokens.
Right.
They used a novel method called claim level reliability assessment, or CLR. How is CLR computationally different from brute force majority voting?
Well, CLR is a highly surgical approach to self-verification. The model generates a set of candidate trajectories, but instead of forcing a separate verification pass over the entire verbose trace, the system extracts exactly 5 critical, decision-relevant claims from each trajectory.
It isolates the load-bearing pillars of the logical argument.
Exactly. The model then acts as its own self-verifier, attempting to falsify just those 5 extracted claims. It generates a nonlinear reliability score based purely on the integrity of those logical anchors.
Which massively reduces token consumption during the verification phase.
Right, while still heavily penalizing any trajectory that relies on flawed intermediate logic. This specific CLR mechanism is what isolates the highest quality path and boosts the model to a 97.1 on AME26 and a 99.2 on Brumo 25.
But to validate their original hypothesis, the reasoning knowledge decoupling paradigm, we have to look at the other side of the coin.
Yeah, the knowledge side.
If reasoning is compressible, but knowledge is expansive, what happens when we test this highly optimized logic engine on GPQA Diamond, a benchmark that requires deep encyclopedic recall of graduate-level sciences?
The GPQA Diamond score, even with CLR activated, lands at 72.9. It is a highly respectable score for a small model, but it is visibly lower than the giant flagship models, which routinely push into the mid to high 80s on that specific benchmark.
And that perfectly closes the loop on their theory. The 3B model has an elite frontier-level reasoning engine, but it physically lacks the parameter volume, the raw synaptic storage to memorize the entirety of graduate-level scientific literature.
Exactly. It proves that the bottleneck in verifiable domains like math and code is not raw parameter count. It is high-quality post-training, diverse solution exploration, and reliable claim-level verification.
Yeah, VibeThinker-3B effectively acts as a parameter scale probe for the industry. It definitively proves that a 3 billion parameter budget is completely sufficient to house a top-tier reasoning engine, provided you engineer the training pipeline with diversity-driven SFT, maxent-guided RL, and mathematically rigorous token efficiency frameworks like long too short.
Yeah.
It demands that we stop viewing small language models as mere deployment compromises for edge devices and start treating them as structurally distinct, highly specialized reasoning instruments. So what does this all mean for you as you design and scale your own ML systems?
Well, if the reasoning knowledge decoupling paradigm is truly the underlying reality of model architecture, that reasoning is highly compressible, while knowledge is intrinsically parameter expansive, it points toward a fascinating, highly modular future.
Okay, what do you mean?
Consider the architectural implications. If we follow this logic to its conclusion, the future of foundational AI might lie in fundamentally separating these systems at deployment. Imagine running a hyper-efficient 3 billion parameter reasoning CPU, that handles all logic, search, and constraint satisfaction natively, but hooks via API into a massive, non-parametric, constantly updating vector database to retrieve its knowledge.
Oh, wow.
Right. Why continue to force our reasoning models to statically memorize the encyclopedia at a training cost of hundreds of billions of parameters when they could simply be taught how to think and given a library card?
That is an incredible way to put it. Maybe reaching the frontier of intelligence isn't about increasing the mass of the star at all. Maybe it's just about the precision of the engine. Thanks for joining us on the deep dive.